There are four basic properties of gases, four things we can measure. Pressure, we use capital P for that. Volume is capital V. The temperature is capital T. And the amount of gas we measure in moles, and that has a symbol N. Those properties are interrelated. If you change one, it's going to affect the others. And the simple gas laws describe the relationships between just two of the four different variables. So we have, for pressure and volume changing, we have one law. And for pressure and N changing, there'd be another law. And T and N be another law. Okay, so you can have a simple gas law describing the relationship between any two of those properties. So the first one we're going to look at is Boyle's law, and this is looking at the relationship between volume and pressure. Robert Boyle lived in the 1600s, and he did some cool experiments with gases. I'm not going to quiz you on his name or when he lived. It's just helpful to have some context. So he used a J-shaped tube, had gas on one side, and he had this sealed off. And he could measure the pressure of that gas relative to atmospheric pressure by looking at the difference in the mercury columns, right? So there's a pressure difference here. This gas has a volume. If you know the inside diameter of the tube and it's a cylinder, you could measure the height and you could calculate the volume that way. So he's got the volume and the pressure. You can increase the pressure on that gas by pouring some more mercury into this side of the tube. It's going to push down on this, and this side's going to come up, and it's going to compress the gas. And we can see now the pressure difference between outside and inside is greater, and the volume has decreased. Again, no technology involved here. Some glassware, some liquid mercury, and a ruler. Very cool. So we've got an inverse relationship. If the pressure goes up, the volume goes down. If the volume goes up, the pressure goes down. They're opposite. So you could graph the data like this, the volume versus the pressure. And you get this curve, which is not, it's not bad, but it's not all that useful. We like it when we can get a straight line out of stuff. It's easier to describe. So Boyle's law can be stated this way. The volume is proportional to 1 over the pressure. And here we're assuming that the temperature and the amount of gas remain constant, because these simple laws look at only two things changing. So the graph of volume versus pressure is curved, but if we graph volume versus 1 over the pressure, we're going to get a straight line. As the pressure increases, volume decreases by the same factor, so the pressure times the volume is a constant, and that gives us this relationship here. So this is how we usually represent Boyle's law. Pressure 1 times volume 1 is equal to pressure 2 times volume 2. So here's volume versus pressure. It's that curve. If we graph volume versus 1 over the pressure, we get this really nice straight line. The intercept is 0, and so we can describe that line as y equals mx, where x is 1 over p. And so that's what leads us to pressure times volume is equal to a constant. That would be the slope. Well, let's think about what the molecules are doing. Here we have a container with a pressure gauge, and the lid can be moved so we can change its volume. We've got the same number of gas particles here, and here what we've done is we've added more weight to the top of this and compressed the gas. So in the first instance, the volume was 1 liter, the pressure was 1 atmosphere. Here, we're squishing it down. The volume now has been cut by a factor of 2. It's twice as small, or half as big, 0.5, and the pressure has doubled. Pressure goes up by a factor of 2 when the volume goes down by a factor of 2. Why does that happen? Why does the pressure go up? Because now we've got the same number of gas particles, but they're in a smaller volume, and so they're going to collide with the sides of the container more frequently, and that's higher pressure. It is not responding. Come on. There we go. So Boyle's law has, oh gosh, now it's doing everything I did before. Fine. Boyle's law has applications in scuba diving. There's a reason they make you take all those classes, because there's so many ways you can kill yourself scuba diving. It's not as simple as it seems. As you descend below the surface of the water, the pressure increases, because water is much more dense than air, and so you've got all this water above you pushing down on you. The pressure increases much more rapidly than it would if you were just going down below sea level in air. So for every 10 meters that you go down, the pressure increases about 1 atmosphere. So here at a depth of 20 meters, this diver is experiencing a pressure of 3 atmospheres. At the surface was 1 atmosphere. For every 10 meters that you go down, you increase 1 atmosphere of pressure. I'm not going to make you remember that. So if you've got a diver down there and he holds his breath and rises quickly to the surface, the pressure's going from 3 atmospheres to 1 atmosphere. What's going to happen to the volume of air in his lungs? It's going to expand by a factor of 3. That could cause some serious internal damage, right? Always exhale when rising, okay? Because the pressure on the outside is changing. Your lungs, your muscles can only contain that air so much, and so you need to let it out as you go up. There's almost an infinite number of problems that could be written for gas laws. Some of them can be very interesting / frustrating for students. And so this is a chapter where critical thinking is important. There are very straightforward gas law problems, and then there are some that require you to think about stuff and put stuff together. And there will be a question like that on the exam, where you have to put ideas together and think critically. So let's look at this problem. The snorkeler takes a syringe filled with 16 milliliters of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? And if the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So it can be helpful in a question like this to draw some pictures. So here we have the surface of the water, and we're starting out up here at the surface with a syringe, and it's got some air in it. And the volume of the air in there is 16 milliliters. And then the diver takes it down here. The pressure increases, and when you put pressure on a gas, it's going to decrease in volume. And so the plunger is going to move down. You're not pushing on it or anything. It's just going to move down because the water is pushing on it. So down here, the volume of the air is 7.5 milliliters. The pressure up here is 1 atmosphere. The question is asking us, what is the pressure down here? So we have volume changing and we have pressure changing. Let's call this volume 1, and let's call this pressure 1, because those go together. And we'll call this volume 2, and this is pressure 2. So there's an equation that relates P1, V1, P2, V2, right? It's Boyle's law, P1, V1 equals P2, V2. These problems require algebra. There's another method using ratios, and if you want to learn that, please come talk to me. I'd be happy to explain it to you. In my experience, using the equation goes better with most students. So I'm going to take this equation, I'm going to rearrange it, and solve for P2, the thing I'm looking for. So I'm going to divide by V2 on both sides. And if you're still iffy on rearranging equations like this, now's the time to figure it out. And if you need help, please ask. So this tells me that pressure 2 is equal to pressure 1 times volume 1 divided by volume 2. So I've got my equation, and then I'm going to put in the numbers. Pressure 1 was 1 atmosphere. Volume 1 was 16 milliliters. Volume 2 is 7.5 milliliters. Always write the units. Look what the units are doing. The milliliters cancel out. So I have 1 times 16 divided by 7.5. So P2 is 2.133 atmospheres. Two significant figures because everything else has two sig figs. Any questions? So the answer to what's the pressure? 2.1 atmospheres. How deep is the snorkeler? This is the trickier part. So down here we've got 2.1 atmospheres. Every additional 10 meters, you increase 1 atmosphere. So that sounds like a conversion factor to me. 1 atmosphere per 10 meters in depth. What was the change in pressure? This pressure minus that pressure, right? So the higher pressure minus the lower pressure that's the change in pressure. You get 1 additional atmosphere for every 10 meters. So we can take that 1.133 atmospheres increase, multiply by 10 meters per 1 atmosphere. And that's going to give us I just lost everything. 11 meters. That's the answer, 11 meters. And now I've got that thing at the bottom, and we're just, it's not advancing.
Just remember it's a cute, fluffy dog.
Charles also did experiments. He looked at the relationship between volume and temperature. He found that the volume of a gas increased when you increase the temperature. The volume of a gas is directly proportional to the absolute temperature. That's the temperature measured in kelvins. So this is really important. And it's probably one of the most common mistakes students make. When you're doing gas law problems, the temperature has to be in kelvins. It will frequently not be given to you in kelvins. It'll be given in Celsius usually. You have to convert it to Kelvin. So here is the expression of Charles' law. V1 over T1 equals V2 over T2. Yay, it advanced. So if you graph the volume of a gas versus the temperature of a gas, you're going to get a straight line. So here's for 1 mole of gas, here's half a mole of gas, here's 0.25 moles of gas. You get these nice straight lines. If you extrapolate them, if you go beyond the actual data and extend that line, what we observe is that all those lines intersect at, would have a y-intercept 0 volume at minus 273.15 degrees Celsius. That's called 0 Kelvin, absolute 0, because it's not possible to have negative volume. If you went past this, then the volume would be negative, and that's not possible. So this is the lowest theoretically possible temperature. We've gotten really close to getting there, but nobody's actually gotten to 0 Kelvin. It's like, well, if that's the lowest theoretical, of course somebody wants to say, well, let's get colder than that. Haven't been able to do that yet. We want to use Kelvin because when we use Kelvin temperatures, we never have negatives, and so we can't end up with negative volumes. And the equation for the line becomes simpler. Instead of y equals mx plus b, the y-intercept b is 0, and so now we get y equals mx. So you have to use kelvins. This is something you can try at home. Take a balloon, put it in ice water, watch it shrink. Take the same balloon, put it in boiling water, watch it grow. When you change the temperature, you're changing the kinetic energy. If the pressure is the same, and the balloon particles, the molecules of the, if the gas particles are moving faster, in order for the pressure to be the same, you have to expand the volume. So you increase the temperature, gas particles move faster. You get more collisions with the wall, more frequent, and each collision is more forceful. So in order for the pressure to remain constant, which is, it's set up so the pressure is remaining constant, then the gas has to occupy a larger volume. By occupying a larger volume, then you get less frequent collisions, and they're occurring over a larger area. I remember being mystified by hot air balloons, because if you blow up a regular balloon with air, it doesn't float. And if you have a balloon that does float, like a helium balloon, and you have a hole in it, all of the helium comes out and it doesn't float. So how the heck can you make this giant balloon with this giant hole at the bottom, filled with air, float and carry people into the air? What? Well, this has to do with volume and temperature. You've got this gigantic burner here that's heating the air. When you heat the air, it expands, right? So if you're expanding the air, it's taking up more volume, same number of particles, the density goes down because the volume's larger. Mass divided by volume is density. If you increase the volume, the density decreases. So by heating the air, you make it less dense. Less dense air floats in the more dense, cool air around it. And that's how hot air balloons work. This is a picture of a balloon in liquid nitrogen. It shrivels up and gets really small. Okay, so let's do a Charles law problem. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? Okay, this is a typical gas law problem. And in the snorkeling syringe one, we drew pictures and stuff. I'm going to show you another technique involving just making a table and collecting numbers into the table. So I'm going to make a table here. And I'm going to call the first row 1 and the second row 2. And I'm just going to go through here and collect numbers. So here's 88.2 milliliters. So I'm going to write that here in this first row in the first box. Sometimes the words tell you what that is. Other times you have to look at the unit. Milliliters is a unit of volume. It also says volume here. So I'm going to call that column the volume column. So this is the initial volume, and then we see that the temperature is changing from 35 to 155. So this is the initial temperature. So the initial temperature goes with the initial volume. So I'm going to write those two on the same line. 35 degrees Celsius. That's the temperature. The temperature changes from 35 to 155 Celsius. So I'm going to write the other temperature down here. And then it says, what's the final volume? Well, what I have now in my table is I have 3 boxes with values and one that's empty. I'm going to call this V2 because it's in column V and it's the second row. V2. This is V1, T1, V2, and T2. Why did I leave this open here? Can we do this with degrees Celsius? No, we can't. We have to convert to Kelvin. So 35 plus 273, it should be 0.15, but your book gets sloppy here. That's going to be 308 Kelvin. And I'm tired, so I'm going to be sloppy too. 155 plus 273, 428 Kelvin. We have to use the Kelvin temperatures. So we've got volume and temperature. We need the simple gas law that has V's and T's in it. V1 over T1 equals V2 over T2. Charles' law. That equation has fractions in it, and fractions mess you up. A lot of students. So cross multiply, get rid of those fractions. So we take the top of one side times the bottom of the other side. V1 times T2. And that's going to be equal to the bottom of the first side times the top of the second side. That's what cross multiplying is. I finished it on here. Technology, you can't live with it and you can't live without it. There we go. Okay. Then we need to rearrange this. We are looking for V2. So I'm going to divide both sides by T1. The T1s on this side cancel out. And then I'm going to copy down that equation. You should always show your work when you're doing these problems. I know that some of you can rearrange that equation just by looking at it. That's awesome. You can take this and go directly to that. That's great if you can do that. If not, write this all out. But the minimum I want you to show is I want you to show the rearranged equation, and then I want you to show it with the numbers in it, and then the result. So 88.2 milliliters. And we want to multiply by T2. You got to be careful here. There's lots of 1s and 2s, and it's really easy to get them mixed up. And then I'm going to divide by T1, which is 308 Kelvin. I look at the units, the kelvins cancel out. So 88.2 times 428 divided by 308. Volume 2 equals 122.56. I'm looking at all of these have 3 sig figs. This is 3, that's 3. Milliliters, and around that to 123 milliliters. Any questions? With simple gas laws, you can often see, did this make sense? We're heating a gas. When you heat a gas, you expect the volume to get larger. And it did. So that's a good sign.